Hey, Dr. O here, and welcome to Chapter 15. We're going to be taking a look at dynamic equilibrium. So what are our objectives for this chapter? Well, we're going to be looking at concepts surrounding dynamic equilibrium, of course, defining it and looking at what goes into that. And then we're going to learn how to express those moments of equilibrium. And we have what's called the equilibrium constant. We're going to figure out how to calculate that. We're also going to learn how to calculate something called the reaction quotient, which is when a reaction is not yet attained that equilibrium, and look at how we can use this reaction quotient to predict whether we're going to see our reaction favor the formation of products or favor the formation of reactants. And then we're going to wrap it up by taking a look at the work of Le Chatelier and applying his principle. And that means we're going to be looking at situations where we not only play with the amount of our gases in our reaction, but we're also going to be playing with volume and temperature. So let's get started. So what you see here on the screen is a picture of hemoglobin, and hemoglobin is a protein, and it's made up of 4 subunits. So here we're seeing, I'll point this out a little bit later, but there's 4 units here. So there's actually a subunit here and another one here, and then another one here and another one here. So each one of these little proteins is exactly what we discussed in the previous section, hodgepodge, about how it's an amino acid strain that's been doubly folded, and it has to be part of some other protein units in order to be functional. But this is hemoglobin. So what's so special about hemoglobin? Well, it's a protein that we find in red blood cells, and its job is to carry oxygen. So within each one of these little protein loop-de-loops, there's a little nugget of hydrogen that will bind to oxygen. And it's going to enhance the amount of oxygen that can be carried throughout the bloodstream. And here's a chemical equation that kind of tells us about it. So in the presence of hemoglobin and oxygen, we will create this other sort of binding called oxyhemoglobin. That's what that's telling you. So the fact that we have hemoglobin and oxyhemoglobin all in one equation says that these concentrations are interdependent. And the relative amounts of each one of these at equilibrium can be calculated into what's called an equilibrium constant, or K. And the deal with K is that a large value of K indicates that a high concentration of products are favored at equilibrium, whereas a small value of K indicates that a high concentration of products is featured at equilibrium. So let's take a peek at what's actually happening with this equation in different scenarios. So here we have our equilibrium reaction, and let's say that we were to add oxygen to this side, to our reactant side. Well, what would happen for a moment with our transformation arrow? Well, when we add this extra oxygen, what we're going to see is the transformation arrow is going to shift to the right. So by adding more reactant, it's going to favor the creation of more product. And we would express that by drawing a larger arrow pointing to the product side. But what about if the opposite is true? What if we were to take out oxygen? Well, let's take a look at that scenario. So if we have the situation here where we've added more oxygen and it's now favoring the creation of oxyhemoglobin, what happens if we were to take out that oxygen? Well, oxygen coming out would then cause the creation of more reactants. And eventually what would happen in either one of these, whether we added more oxygen or took oxygen out, we would have the reestablishment of an equilibrium at some point. So just because you take out a certain amount of oxygen doesn't mean that you're going to always be favoring the creation of more reactants as a result of that. There will be another equilibrium that gets established where the rates are now equal, so that the rate at which reactants are made will be the same as the rate at which the products are made. It's just that when you have certain scenarios where the concentrations are going to tell you which one of those is favored, because there's going to be a point at which we see the products being favored, and there's going to be concentrations where we see the formation of reactants being favored. So a great example of this sort of dynamic is what's happening in the lungs. So In the lungs, what we see happening is that we have a high concentration of oxygen in the lungs coming in contact with blood. And this blood, from the experience of the blood, it's going to have relatively low levels of oxygen. And so for the blood, that's where we're going to find hemoglobin. So for blood, the equilibrium is going to shift to the right as we get the uploading of oxygen into the bloodstream. And what that means is that hemoglobin and oxygen are going to combine to form more oxyhemoglobin as a result. So we're going to see that equation shift to the right and favor the formation of the product. Now, what happens in the tissues? Well, something else different happens in the tissues because now we're offloading oxygen. So what happens in the tissues is that we're going to have the offloading of oxygen. That's how we explain concentration of oxygen being low. And when that happens in the blood, the equilibrium is going to now shift to the left in favor of the formation of the reactants. And this is going to be what favors oxygen leaving the bloodstream and going out into the tissues. So that means that our hemoglobin is going to break down and is going to result in this free oxygen, which can now go out into the tissues. And it is by this mechanism that we see oxygen being transported around the body. So it binds to hemoglobin, and then when the conditions are right, when the partial pressures are in such a way, when the concentration of gases are such, it will cause the hemoglobin and oxygen to unbind and free up the hemoglobin, the oxygen, so that it can then be released into the tissues. Now, there's another unique situation that involves hemoglobin, and this is the hemoglobin in the fetus. Fetal hemoglobin equilibrium constant is larger than that of an adult's hemoglobin equilibrium constant. And the reason for this is that fetal hemoglobin has a greater affinity to bind oxygen than adult hemoglobin. And so what happens here is that as oxygen is transferred to the fetal hemoglobin from the mother's hemoglobin in the placenta, the baby's binding capacity is greater. So it has to actually be, if we think about this, it has to be as great, if not greater than the mother's, in order to create that wicking action that is needed to make sure that oxygen gets offloaded into the baby's blood supply. So I guess the question then becomes, what's the difference between adult hemoglobin and fetal hemoglobin? Well, here's a picture of adult hemoglobin, and here's a picture of fetal hemoglobin, and hopefully that's apparent to you what the difference is. No, I'm just kidding. I know that you can't look at these and tell me what's going on, so I'm going to give you the quick tour. So what we see here with the adult hemoglobin is that we've got 4 protein groups that are comprising this hemoglobin. We have 4 that are also comprising the fetal, but they're different. So in the adult hemoglobin, we have an alpha hemoglobin here and then another alpha down here at the bottom. And in the fetal hemoglobin, we also have an alpha protein, and then we also have an alpha protein in the same position. But in the adult hemoglobin, the other set of proteins that are present are beta protein chains. And in the fetus, they're called gamma protein chains. And the difference between the beta and the gamma proteins is one amino acid in position 136 in the amino acid chain. That's all. And that one amino acid difference is enough to change the conformation, to change the shape of fetal hemoglobin so that its binding capacity, its affinity for oxygen, is far greater than that of the adult hemoglobin. So let's articulate what's actually happening in a dynamic equilibrium situation. So when a reaction starts, the reactions get consumed and products are made. And as the reactant concentrations decrease, the product concentrations increase. Because remember, this is all typically happening in a container of some sort. It might not necessarily, but we can think of it that way. Now, as the reactant concentration decreases, the forward reaction rate of the entire chemical process is actually going to slow. So that tells us that there's a relationship between the momentum of a reaction and the concentration of the reactants. Now, eventually the products can react to reform some of the reactants, assuming that the products are not allowed to escape from our container. Now, as the product concentration increases, the reverse reaction rate has the ability to increase as well. So if we think about this, we have depleting reactants, slowing down the forward momentum of a reaction, and we have increased concentration of products now starting to create a gradient that is slightly favoring the creation of reactants. Now the um, processes that proceed in both the forward and reverse directions are said to be reversible. And we know that we can write that with this double-headed arrow. So what we've just described, talking about the concentration changes and the rates of reaction being altered, that's what's happening in a dynamic equilibrium situation. Now, chemists use two types of arrows that tell us the degree to which a reaction has undergone some completion. And one of those is the single-headed arrow, which indicates that all the reactant molecules are converted into product by the end of the reaction. And then the other one is that double-headed arrow that indicates that the reaction is in equilibrium. So what this one tells us is that we have a rate of reactants converting to products, and there's also a rate at which products are reconverting back into reactants. So that's what that double-headed arrow is telling us, and that's what we're going to be looking at mostly in the rest of this chapter. So as I just said, dynamic equilibrium is that condition where the rates of forward and reverse reactions are equal. And because the forward reaction rate slows and the reverse reaction accelerates, eventually they're going to reach the same rate as we look at the reaction occurring from start to finish. So that's what's happening there. Now, once the reaction reaches this equilibrium, the concentrations of all of the chemicals involved are going to remain constant because the rate at which the chemicals are being consumed is going to be equal to the rate at which they are being made. Now, an important note here is that just because the concentrations remain the same doesn't mean that the concentrations of each product is equal to each other. Because remember, we can have a scenario where equilibrium favors the production of products, so we're going to have relatively more products than we have reactants, or we could have a situation where equilibrium favors the creation of reactants, in which case we'd have greater concentrations of reactants than we would products. Now, in any sort of reaction, as the concentration of the products increases, we're naturally going to see a decrease in the concentration of the reactants. So we always start off with a whole lot of reactants, and at the very beginning we're going to have just a tiny bit of products. And as this reaction moves forward, we're going to see a decrease in our reactants and an increase in our products. Now, at some point, we're going to see such a decrease in our reactants that we're actually going to start to see a decrease in the forward momentum of our reaction. And even though we're still going to see an increase in our products. And at some point, we are going to see such an increase in our products that eventually a reverse reaction is going to be reestablished or is going to be established. So therefore, we can say that as the rate of the forward reaction decreases, the rate of the reverse reaction is going to increase. And this is the basis of our dynamic equilibrium. And we could say that the rate of the forward reaction is now equal to the rate of the reverse reaction. And this also means that the concentrations of the reactants and the concentration of the products is no longer changing. It doesn't mean that they're the same. It just means that they are now at a state where they're the same. The concentrations remain the same over time. So as I've said several times, the equilibrium does not mean that equal amounts of reactants and products exist. It just means that the rates of the forward reaction is equal to the rate of the reverse reaction. So that's just an important concept to get into your heads. Now, what's going to happen then is that some reactions at equilibrium are going to favor most of the reactant molecules being consumed. And when this is the case, we would say that the position of the equilibrium favors the product. So it's going to look something like this, where we're going to end up with a small concentration of the reactants and a large concentration of the products. And at that sort of distribution of concentrations, we're going to see an equilibrium, a dynamic equilibrium established. Now, the other possibility is that we're going to establish an equilibrium when only a small amount of the reactants are consumed and there's just a small amount of product present. And in this case, it might look something like this, where we have a large concentration of the reactants and a small concentration of the products. Now, when we do the calculations in a little bit and look at how to establish an equilibrium constant for each of these reactions, we're going to see that a large concentration constant is going to favor the products, and we'll see how that math works out, and that a small concentration constant is going to indicate that it favors the formation of reactants. So we're going to prove that in just a little bit. When calculating the equilibrium constant, you're creating a relationship between the chemical equation and the concentrations of the reactants and the products. And we call this relationship the law of mass action. So let's take a look at this in detail. So let's say that we have an equation like this, and you can see we have capital letters and we have small letters. In this equation, the capital letters represent the reactants and the products, and the lowercase letters represent the coefficients. And because remember, we have to have a balanced equation in order to move forward with this. And when we put them in our equation in order to calculate our constant, we always put the products over the reactants. So what we're looking at here is we're taking the concentration of our products. We might have two, we might have more, we might just have one. And we're going to raise it to the power of its coefficient, which might be 1, might be 2, might be more. And we're going to do that for all the products, and then we're going to do the same thing for the reactant. So we're going to take a concentration of the reactant and multiply and raise it to the power of its coefficient. This is how we calculate the equilibrium constant for a balanced equation. And this does not have any units. Yay. So for a reaction where we have two dinitrogen pentoxide molecules, that would render 4 nitrogen dioxides and an oxygen molecule. So if we wanted to write the equilibrium constant for that, what we would do is we would take our products, which would be nitrogen dioxide, raised to the 4th power, and we're talking about the concentration, which we haven't been given yet, and oxygen, only one of those, so there'd be a power of 1 here. We don't have to write that. And then we have 2 of these dinitrogen pentoxides. So that's how you would write that. Now, once we get the concentrations of this, we'll be able to actually plug in the numbers and do a calculation for K. But initially, this is where you need to be at this point in this lecture, just being able to set up the concentrations in order to eventually calculate your concentration, your equilibrium constant. Now, a little bit ago, I said something about when the value of K is large and when the value of K is small, and what that will tell us is being favored in a reaction. And what we see here is the scenario when K is large, when K is greater than 1. So when the value of K is greater than 1, when the reaction reaches equilibrium, there's going to be more products present than the reactants. So what we can say then is that when K is greater than 1, the creation of products is favored. So in this case, we look at the concentrations, and we're going to have a lot more of our product than we will reactants, and that's how we're going to get a large K, because 10 to the 19th is a large number. But what happens if things are going the other way? Let's take a look. So when the value of K is less than 1, not necessarily negative, but less than 1, then when this reaction reaches equilibrium, there's going to be more reactant molecules present than what we see with the products. So we could then conclude that when K is less than 1, the reaction favors the creation of reactants. And if we look at this K, we can see that it is considerably smaller than 1 because we have a negative exponent here. So if we think about this, we've got now a very small number and a very large number, and that's how we're going to end up with a number that has a whole lot of numbers to, a whole lot of zeros to the right of the decimal number. That's how we're going to get that. So that's what the value of K can tell us. By looking at the value of K, we can say, oh, well, this is a reaction that's going to favor a higher concentration of products, or it's a reaction that's going to favor a higher concentration of reactants. So we've established that the equilibrium constant for a reaction such as this one will be set up like this, where we have the products on top and the reactants on the bottom. But remember, our reaction can not only go forward, but it can also go in reverse. So what happens to the equilibrium constant when our reaction is going in reverse? Well, let's take a look at that. So technically, when our reaction goes in reverse, our products and our reactants are swapping places. So then we could say that the equilibrium constant for a reaction going in reverse would reflect that, where we had what was once our reactants now in the products position, and what were once the products now in the reactants position. Everything is elevated to or raised to the coefficient. So when the reaction is in reverse or going backwards, the equilibrium constant then is inverted, and we can say that the equilibrium constant of a reaction moving forward is equal to 1 over, or the inverse of the equilibrium constant of the reaction when it's going in reverse. Now, one of the things that we do sometimes to our equations is we multiply them by a factor. So what happens to the equilibrium constant when that happens? Well, the equilibrium constant is going to be raised to that factor. So let's say that we have this equation right here where we have A plus B is going to be equal to C, and we're in dynamic equilibrium. Then we would know that our equilibrium constant would look like this. We've already gone through that. But what if we multiply that same equation by 2? Well, in this case, we multiplied the reactants, both reactants, by 2 as well as the product. So our equilibrium constant now is going to look like this, and you'll notice that we have 2 in all of the raised factors, all of those. So that's one way to write it. And of course, there's another way to write it that would look like this, where we just take everything and we raise the whole thing to the power of 2. So then we conclude then that our initial equilibrium constant is going to be equal to the second equilibrium constant raised to a factor if we multiply our equation by that factor. And we have one more scenario to consider with regard to our equilibrium constant. So let's say that we have a reaction that's going to take a couple of steps to get there, and we have to write a couple of different equations. How do we combine those equations in order to get the equilibrium constant? Well, what we would have to do is we would have to take the product of the equilibrium constants of all of the equations involved, which in this case are saying the old equation. So let's see what we mean here. So let's say that we had a two-step process where we start off with reactant A to get this intermediate B, and then we use intermediate B to get to C. Well, to create an equilibrium constant to get from A to C would involve the following steps, where we start off with our first reaction, and then our second reaction. And as our rules say, we have to take the product of the equilibrium constants of these two equations. So when we do that, it would look like this. Now I see repeating terms. I see a B in the numerator, a B in the denominator, so we're going to cross those out. And we can simplify our reaction to say that our new equilibrium constant is going to be equal to the C over the A. Now that's what works for this one, but this is another consideration that we would have to take into play if we had multiple steps in order to get our ultimate product. Now we know that the concentration of a gas in a mixture is going to be proportional to its partial pressure. And we could therefore say the equilibrium constant can also be expressed as a ratio of the partial pressures of the gases. So if we had an equation that looked like this, we could express the equilibrium constant as a ratio of the concentrations of the products and the reactants, or we could express it as a ratio of the partial pressure of the products and the reactants. Now, the values of these two equilibrium constants, that based upon concentration and the other based on partial pressure, are not necessarily going to be the same because there's going to be a difference in units. What we do get is the point where we have an equilibrium between the two when the difference in the moles of the products and the reactants is equal to 0. All right, so when we calculate the partial pressure, when we use partial pressure to calculate the equilibrium constant, we have to make sure that the units that we're using are atmospheres. And the relationship between them will be as follows. So this looks very much like our gas law, where we had the use of the gas constant R, and in this case, R is equal to 0.08206 liter atmospheres over moles Kelvin, and T would be the temperature, and then this delta N would be the difference between the number of moles of gaseous reactants and the number of moles of gaseous products. Now we're only looking at the gaseous components involved in the reaction in this case. Let's take a look at this problem. So we're being asked which of these reactions does the equilibrium constant for the partial pressures equal the equilibrium constant for the concentrations, and we have to choose among these three possible equations. Well, let's first revisit the concepts here. So we know that the equilibrium constant for the partial pressure is going to be equal to that of the concentration when the difference between the number of moles of the gaseous reactants and the number of moles of the gaseous products is 0. So that means we look only at gaseous reactants and gaseous products. In this first equation, that would be carbon dioxide, that is our only gaseous reactant, and the gaseous product would be oxygen. In the second equation, these would be our reactants and products, only things that are gas. And then in the third equation, we have two gaseous products. So let's go back to the first equation and see how many moles we have of gaseous reactants, how many moles we have of gaseous products. So if we look, we have 2 moles of carbon dioxide, but we have 1 mole of oxygen. 2 does not equal 1, so this is not our answer. Let's look at the second one. Here we have 3 moles of carbon monoxide, and here we have 3 moles of carbon dioxide. Hey, that looks pretty good. We got 3 moles over here and 3 moles over there. What about our last one? Well, we have no moles of reactant, and we do have 3 moles of product, so that's not going to work. So our only answer could be number 2, where we have the same number of moles of reactants as we do moles of product. So the conceptual connection problem that we worked demonstrated that we could have an equation and a chemical reaction involving substances that are in different states of matter. So such as a solid and a gas going into a reaction together, or we didn't see this in the conceptual connection, but we could have a liquid and a gas going into a reaction together. So then we have to ask ourselves, what happens when you have heterogeneity existing in your chemical equation? Well, concentrations of pure solids and pure liquids do not change during the course of a reaction. Now, the key word here is pure, because it's possible that we could have a mixture, a solution, and what's in the solution would actually be something that we would count towards our concentration. But because the concentrations of these pure substances don't alter, they don't get included in the equilibrium constant expression. So for a reaction like this, where we have carbon dioxide gas going into a reaction with water, water is going to be our pure substance, carbon dioxide is a gas, but then we have hydrogen in aqueous solution and carbonate ions in aqueous solution. So our reaction, our equation rather, for the equilibrium constant is going to look like this, where we take our products, which are our hydrogen ions and our carbonate ions and our carbon dioxide gas, and that all gets included in our expression. What does not get included is water, because it is a pure liquid. Now, up until this point, we have just been talking about how to set up equations in order to get the K, to get that equilibrium constant. Now, we're actually going to find some values to plug in there. So how do we do that? Well, the most direct way is to actually just measure the amounts of the reactants and the products that you have. And we can't do that, but we can certainly have that information supplied to us. So the equilibrium mixture then is going to have different amounts of reactants and products, but the value of the equilibrium constant is always going to be the same across all of the equations. Hopefully that makes mathematical sense. Then we're going to use stoichiometry to determine the equilibrium concentrations of everything provided, and we can do that if we know the initial concentrations and one equilibrium constant. We're going to demonstrate that in just a second. And then we're going to use the change in the concentration of the materials in order to calculate our values that we're going to use to calculate our equilibrium constant. So actually, let's do that. All right, so to demonstrate everything that we just talked about, we're going to work example 15.5. And we're going to take this reaction, and then we're going to actually be given some measured values. So we have a reaction at a constant temperature, and it's going to contain a concentration of carbon dioxide that is 0.5 moles per liter, because remember that big M stands for molarity, which is moles per liter. And we have 1 mole per liter of hydrogen gas. That's our concentration. And that's part of what we need. So we know our initial values, and we need at least one value at equilibrium, and they give that to us in the next line. So at equilibrium, carbon monoxide comes in at 0.15 moles per liter. And now they're asking us to calculate the equilibrium constant. We can do that because they've given us enough information. So the process that we're going to do this by is as follows. So the first thing we need to do is we need to set up an ice table. That ice table is going to have the initial concentration of our products and reactants, and we'll probably have to calculate the change that took place, but because we're given a concentration at equilibrium, we can fill that in. So we're looking at initial values, a change in concentrations, and then concentrations at equilibrium. So let's bring up our table. So there's our initial, change, and our at equilibrium. So that's what the ice stands for. And then we're going to bring up our balanced equation. So we can see that we need to have a column for the concentration of carbon monoxide, one for hydrogen gas, and one for methanol. All right, so we're given the initial concentration of carbon monoxide is 0.5. We don't need to include the units here. We're going to know that that's what they are. We're given an initial value for hydrogen gas, and we know that before the reaction even takes place, we're not going to have any methanol yet. So we're able to easily fill in all of our initial values. Now what we don't know is the change, but we do know the concentration of carbon monoxide at equilibrium, and that is 0.15. So this is the first step at being able to calculate that equilibrium constant, is starting to fill out this table. So let's see what we do next. All right, so what we're going to do next is we're going to look at the reactant or the product. In this case, it happens to be a reactant. That we know the initial concentration and the equilibrium concentration, and we're going to calculate the change. So for us, that's going to be carbon monoxide. So we know initially it came in at 0.5 moles per liter, and we ended up with 0.15. So if we do the math, the difference here is a loss of 0.35 moles per liter. All right, so far so good. All right, now we're going to use that change that we calculated in the step previous, and we're going to use the stoichiometric relationships from our balanced equation to determine the changes in concentration of all the other members of our equation. So for hydrogen, because we have 2 hydrogens, we're going to multiply the change by 2, so that's going to be 2 times 0.35, and we have 1 methanol, so that's going to be 1 times 0.35, and this time this is going to be who gained it. So keep in mind the loss is happening on the left of the transformation arrow, so these are going to be losses, and the gain is going to be on the right side of the transformation arrow. Okay, next we're going to sum each column for the reactant and the product to determine the concentrations. So here we've just taken 2 times 0.35 and we get that 0.7, and we can do the math there. And then if we do the math with methanol, we end up with 0.35. So now we have our concentrations. Hallelujah, we have our concentrations at equilibrium. Now at this point, we can employ this equation that we've been dealing with over and over, just plugging in concentrations and giving whether it's a product or whether it's reactants. So now we actually get to plug these numbers in from our ice chart. So let's do that. So we can see we have our 0.35, that's our only product. And then our 2 reactants are 0.3 and 0.15. And we're going to square our 0.3 because remember from our balanced equation, we have 2 hydrogens. So that's where that square comes from. And now if we do the math, we can actually come up with a value for our equilibrium constant, and it's equal to 26. So what if we have a reaction that's been going on for a while and we don't really know where we are? We don't know if we're still in the initial stages of reactants moving into products, or if we've already kind of met that apex and now we're starting to see the reverse reaction take place, because that could be a possibility. Well, if a reaction mixture containing both reactants and products is not at equilibrium, the question becomes, how do we know which direction it will proceed? Well, there's a way to figure that out. And the answer is that if we take the current concentration ratios and compare those to the equilibrium constant, that will give us some clue of where we are in the process of the reaction. So then the question becomes, what is that current concentration ratio? Well, that's what's called the reaction quotient. And the reaction quotient is very much like the equilibrium constant, where we would take the concentration ratio of the products raised to the power of their coefficients over the reactants raised to their coefficients. But instead of calling it the equilibrium constant, we just call it the reaction quotient. So how would we actually go about putting together this reaction quotient? Well, if we had a reaction going on like this, and let's say that everybody here's a gas, that'll make it nice and easy, then the way that we would calculate the reaction quotient looks like this. And just at first glance, this looks suspiciously like that equilibrium constant. Well, it's because it's pretty much the same formulas. But the difference is what we're calling it. So here we're calling it the quotient to let our reader know that we recognize that this is not a reaction that is now at equilibrium. It's somewhere in the process and we're not sure. So if we look at this, we have our products. In this case, we're looking at the concentration. So we have the concentration of our products raised to their powers, or they're raised to their coefficients, and the reactants raised to their coefficients. Or if we have that information, we could use the partial pressures of the products raised to their powers, and the partial pressure of the reactants raised to their powers. So the big difference is how we communicate what it is that we're calculating. And the Q lets our reader know that we're coming up with a reaction quotient and not the equilibrium constant. So what are these numbers telling us? Well, in order for us to be able to know what these numbers are telling us, we have to have some idea of what the equilibrium constant is, because it's going to be a comparison. So let's take a look at what these numbers could be telling us. Let's look at that on the next slide. So what is all of this telling us? Well, if our quotient is greater than our constant, then the reaction is going to move in the reverse direction, and we're going to see the increase in the reactants and a decrease in the amount of product that we have. And then the opposite would be true. If the quotient is less than the constant, what we would see is the reaction moving forward, and we'd see a decrease in the reactants, but an increase in the products. Now there's still a couple more possibilities here. What if our quotient is equal to K? Well, then we have just managed to catch it at that magical moment when everything is in equilibrium. And what if our quotient is equal to 0? Well, then it means that we have a mixture that's just nothing but reactants, and this means that it's going to move forward in the forward direction, and we're going to see the creation of the products. And then there's still one more possibility. What if our quotient is equal to infinity? Well, then our mixture contains just products, and that means the reaction is going to start to move in the reverse direction. So this is how we're going to take our quotient that we have and our constant that we've been given or maybe even calculated previously, and do the compare and contrast and figure out where we are with our current reaction. So we're at the point in this chapter where we can actually find an equilibrium concentration given the equilibrium constant and some initial concentrations or pressures. And we're going to use the ice table in order to do that. So one of the things that we need to be able to do is, first of all, decide which direction the reaction will proceed. So if we're given our K, then it's up to us to calculate the Q, which we can do if we're given some concentrations or partial pressures. And we have to use the ice table to do that. So that means that we're going to have to define the changes of the materials involved, our reactants and our products, in terms of X, and then use the coefficient from the equation as the coefficient for X in our ice table, and making sure that X is positive for materials on the side of the reaction where it's proceeding to, so where it's going to. So it's not necessarily reading from left to right. It could be going from right to left, because remember, these are reversible reactions, which means that then X has to be negative for the materials on the side of the reaction where it's going away from. So if we are having a reaction that is moving from reactants to products, then our reactants would be decreasing, which would give them a negative number, and our products would be increasing, which would be positive. However, if our reaction was going in reverse, then our products would be losing, so we'd be losing products, make their values negative in the coefficients, and the reactants would be positive. And then we're going to solve for X, and we're going to use that quadratic equation to do that. So let's see what else we have to address here before we actually work a problem. Now we've looked at this ice table before, and you might remember that the I stands for the initial amounts, the change in those amounts as the reaction proceeds, and then the equilibrium constant. And so what you're going to have across the top is you're going to have the concentrations of your products and reactants, and then you're going to have any amounts that you're given, usually the initial amounts, and then you'll figure out if there's something at equilibrium or if you're given a change, and then you'll be able to fill in the rest of this. So let's take a look at a problem. So we're being asked to consider the reaction between dinitrogen tetraoxide and nitrogen dioxide. And if we read through, we have one concentration value given right here for nitrogen dioxide. And we're being asked to find the equilibrium concentrations at this particular temperature right there. Oh, and we're given the equilibrium constant when we have the concentrations. For the concentrations. All right, so what is the first thing we're going to do? Well, we're going to use the balanced equation, there it is right there, and prepare our ice table. So here's our ice table, and we're going to plug in our two substances, our reactants and our products. Now we're only given one initial value, and that is for nitrogen dioxide, which means that we are at 0 for dinitrogen tetraoxide. So at this point we have completed everything that we can for this table. Now step 2 would have us calculate the reaction quotient for what we have going on. So we're taking that snippet of time right here, the snippet of time where we have all nitrogen dioxide, no dinitrogen tetraoxide, and we're going to calculate what our Q is and compare it to our K. So in order to do that, we're going to be using this equation right here, where nitrogen dioxide is considered our products because it's on the right side of the transformation arrows, and dinitrogen tetraoxide is the reactant. It's on the left side of the arrow. And if we plug in the values, here's our value for nitrogen dioxide, and we're going to square it because we have two of them. You have to remember those coefficients, raising it to the coefficient. And we have 0 because we have nothing for dinitrogen tetraoxide. And when we do this math, we're going to get that our reaction quotient is equal to infinity. Now we know something about this, don't we? We know that when the reaction quotient is greater than K, that our reaction is going to proceed to the left. Now let's think about this for a second. What we're being told is that the only thing that we have currently is this, nitrogen dioxide. What can nitrogen dioxide make? Well, if in the reverse direction, it will make dinitrogen tetroxide. So if all we have is nitrogen dioxide, then it should make sense that this reaction is going to move to the left and unmake the products and remake the reactants. All right, step 3 says that we're going to represent the change in concentration with regards to X. So what that means for us is that we know that there is going to be a loss of nitrogen dioxide and a gain of dinitrogen tetroxide because this reaction is proceeding to the left. And the way that we would write that is first off like this. So we would have a negative X, but we have to have a 2 in front because we have a 2 right here. And then we would represent the gain here for dinitrogen tetroxide like so. All right, now what? Now we need to sum each column for the reactant and each for the product and come up with some algebraic relationships with X. So let's do that. So now we're going to add 0. We're going to add 0 and positive X. That's good. And then we're going to add 0.1 and subtract negative, or we're going to subtract 2x. So now we have these two values to move forward. It's starting to look like something we can use our quadratic equation with, doesn't it? Okay, now we're going to substitute the expressions that we came up with for the equilibrium concentrations into the expression for the equilibrium constant, and we're going to use the quadratic equation for that. So here we have our reaction, and now we have some new concentrations or some ending concentrations for each of our concentrations. So here is from our table for nitrogen dioxide, here is our concentration, and for dinitrogen tetroxide, here is our concentration. And these came directly from our table. Now, if we plug in the value, the given value of our equilibrium constant, now we can go somewhere. All right, so what we need to do is we need to be able to put this in quadratic equation form, which means we need to do a few things. We need to move this value to the right side of the equations, the equal sign, and then as we see over here, we're going to have to isolate X. So let's do this in a few steps. So the first thing we're going to do is we're going to multiply by X, everything by X, which means that we'll get rid of it in the denominator here, but it ends up showing up over here. And now we can move this value to the right of the equal sign. And by doing that, we've basically just flipped it around. So now we have a 0 on one side of the equal sign. And if we look at what we've done, we'll have to subtract 0.36 from this side, which means we have to subtract it right here as well. And when we do that, we're going to end up with 0.76, a negative 0.76, which we have right here. And here is our plus 4x squared. And then here is our positive 0.01. So we've done all of the steps that make sense in order to get 0 on one side of the equation sign and all of our terms on the other side, except that in this step we reversed it so that it looks a lot like this right here. All right, now we can isolate X using this formula right here. So what this means then is that we have to look at our 4 as our value of A, our 0.76 as our value of B, and 0.01 as our value for C, and we'll plug those values in right there. So there's our equation we're going to use, and here we go. So here's our B, it's a negative, and it goes into the equation as a negative, and it repeats here, and then we multiply 4AC. So 4A, A, C, and C, and then 2A. So here's our 2, 4 is our A. And now we do the math. And when we do that, we can, in one scenario, we will subtract And in one scenario, we will add, and that's going to give us two possible values for x. So x can be equal to 0.176, or x can be equal to 0.014. Okay, now with our two values of x, we're going to substitute x into the expression for the equilibrium concentrations, those values that we calculated with our ICE table, and see what we get. Now when we do that, we're going to reject one of the values of x. We're going to reject the value of x equal to 0.176, because when we plug it in, it's going to give us a negative concentration for nitrogen dioxide. So we're not going to use this value. It's erroneous. It doesn't mean anything to us. But if we use the other value of x, we actually get concentrations that make sense in the real world. So for example, here we have our concentration value that we calculated with our ICE table. If we use 0.014 right here, here's our equation, and we end up with 0.072 moles per liter for our concentration of nitrogen dioxide. Now if we do the same thing for dinitrogen tetraoxide, we can see what its value is. So now we've calculated, using the ICE table and our understanding of the relationship of these variables, using the quadratic equation, to come up with these concentrations. So now we want to check our answer by substituting the calculated equilibrium values, these values, into the equilibrium expression and then comparing it to the given equilibrium constant K. So let's do that. So here is our equation, and we're going to take the value that we came up with for nitrogen dioxide, and we're going to square it. And then we're going to take the value that we came up for the concentration of dinitrogen tetraoxide and put that in there. So our equation looks like this. And when we do the math, we can see that our value of K, as we calculate it, our value of our equilibrium constant comes up to 0.37. Well, the given value ends up being 0.36. And since our calculated value is really, really, really close to the given value, we're going to consider that the answer valid. So it doesn't have to be precise, but it has to be pretty close. If we came up with something that was like 3.9 or 0.4, we might start to think that we were out of the ballpark on it. But the difference between 0.36 and 0.37 is valid. Now we've talked about a lot already that once a reaction is at equilibrium, the concentrations of the reactants in the products are always going to remain the same. Now, what happens if you disturb it? Well, if the conditions are changed, then the concentrations of all the players are going to change until equilibrium is once again restored. So this is a principle that was demonstrated by Le Chatelier. Furthermore, the new concentrations may be different in our new equilibrium, but the equilibrium constant, which tells us about the proportionality of the products and the reactants, will remain the same unless we change some other dynamic at work in the system, such as temperature. So Le Chatelier's principle guides us in predicting the effects that changes can have on the position of equilibrium in a system that is in equilibrium. So he was playing around with figuring out, well, I've got a system in equilibrium, and what happens if I add more reactant? Well, what happens if I remove reactant? What happens if I add more product? So he was seeing what was happening in those scenarios. There were other variables that he could have played with, such as volume, temperature, pressure that the system was at, in addition to the concentrations of the products and the reactants, and he did all of that. And he basically found that a system has a tendency to minimize a disturbance. Once it's at equilibrium, a system will have a tendency to adjust so that it minimizes the disturbance to that equilibrium. In order to understand what Le Chatelier was trying to demonstrate, we have to look at disturbing systems that are in equilibrium. So what if we were to do something like add a reactant? Well, if you add a reactant, you have to make sure, first of all, it's not a solid or a liquid, because otherwise the moles won't count. And if you do add additional moles of a gas, then you have to do a new calculation for an equilibrium constant, because remember, it's the ratio between the concentration of the products and the concentration of the reactants. And that's all easy enough to do. We know how to do that. But we need to ask ourselves a question. How will this affect the rate of the forward reaction? Well, adding the reactant initially is going to increase the rate of the forward reaction, but it will have no initial effect on the rate of the reverse reaction. The reaction then will proceed to the right until the equilibrium is restored. So what we're saying then is if we have a system that's currently in equilibrium and we add more reactant to it, what we're going to see is our rate of forward reaction moving forward is going to increase, but not necessarily see a decrease in the reverse reaction. So another important question to ask is, how will this affect the rate of the reverse reaction? Well, at the new equilibrium position, you will have more products than before, less of the non-added reactants than before, and less of the added reactant. But you won't have as little of the added reactant as you had before the addition. So let's actually see what we're talking about there. So at the point where you have added your reactant, your new reactant, you will now have this equation. So you have the added reactant plus the reactant that was already there, and we have now shifted the equilibrium to the right and we're making more product. So at that moment where we've added this, and we've allowed some of the product to be made, at the new equilibrium, what we're going to actually see happening is, first of all, the establishment of a new equilibrium. And what we're going to see in our container is that we'll have more product than we had before, but some of the initial reactant that we had will get used, so there'll be a little bit less of that. And some of the added reactant will also be used, so there'll be less of that. So that's really what we're saying here, is that now we're looking at the concentrations. Together, the ratios will be the same as what we know the given was for the equilibrium constant, but the concentrations of the stuff that we're using to get there is going to be a little bit different, because now we have to include this player here. Technically, it would all be included here, but we would have its source being what we added. Now, the third question we need to ask is all of this that's changing, will that affect the value of our equilibrium constant? Well, the new equilibrium position, the concentrations of the reactants and the products are going to be such that the value of the equilibrium constant will be the same, as it should be, because remember, it's a ratio. So let's put all of this together. So let's say that we have our reaction that is at equilibrium, and let's assign some values. Let's say that we have 4 moles per liter of the reactant. We have the same for the product. This is not always going to be the same when we have something at equilibrium. It doesn't always mean that the amount of reactant will equal the amount of product. I'm doing it here just for simplicity's sake. So with these concentrations, we can calculate the equilibrium constant. So our equilibrium constant would be the amount of the product over the amount of the reactants, or the concentration of the product over the concentration of the reactant, and we can see that it would be equal to 1 in this case. All right, well, that's great. So let's say that we were going to add the reactant. And let's say that we added 4 moles of reactant. Now we know that initially that it's going to shove the arrow right, going to make the equation go towards the right, and that is going to increase the amount of product that we have. Now we're not given any values at this point, but if we were, another thing that we could calculate is the quotient. Given the concentrations at any given moment, and we could predict whether our equation was going to continue to the right or whether it was going to start to reverse and go to the left. But we're not given those values, so let's not worry about that. What we do know is that this equation at some point is going to reestablish an equilibrium, and we're going to have different values for the amount of reactant that we have and the amount of product. So let's say that instead of having 4 moles per liter of our product, let's say that we're going to have a little bit more product now, because we've pushed the equation to the right, and now at our equilibrium we're going to have 4 moles per liter of product. We're going to have a little bit less of the original amount of reactant that we started with. So let's say that we end up using a mole of that. Now we only have 3 moles of our original reactant. And let's say that we also consume some of the moles of the added reactant, so that we're down to 3 moles of that as well. Well, if we look at at all of our concentrations, we have 6 moles per liter on the right of the transformation arrow, and we also have 6 on the left. So you can see why I'm keeping my numbers simple. So we could calculate this new concentration, this new equilibrium constant, and it would be 6 moles of product over 6 moles of reactant, and we would still have the same value, which would be 1. So that's how putting all of this together would work. So as we've seen, adding a reactant will decrease the amounts of the other reactants, and it will increase the amount of the products until a new position of equilibrium is found with the same equilibrium constant. Now, removing a product will increase the amounts of the other products, and it will decrease the amounts of the reactants. So hopefully that makes a little bit of sense. So overall, we can conclude then that equilibrium shifts away from the side with the added chemicals or towards the side with the chemicals removed. So remember, adding more of a solid or liquid does not change its concentration. Therefore, it's not going to actually have an effect on the equilibrium. We're only looking at the gases. So adding a gaseous reactant is going to increase its partial pressure, causing the equilibrium to shift to the right. Now, increasing its partial pressure will also increase its concentration, but it doesn't increase the partial pressure of the other gases in the mixture. Now, what if we added an inert gas to the mix? Well, it's not going to have any effect on the position of equilibrium because it doesn't affect the partial pressures of the other gases in the reaction. So an inert gas has no effect, kind of like a liquid or a solid. So there are other variables that we could shift around in these scenarios, and one of them is volume. So what if we decrease the volume of the container? Well, decreasing the volume of the container will actually increase the concentration of the gases in the container. Because remember, gases are moles per volume. And that means it's going to increase their partial pressures. Now, that's only the effect of gases. It's not going to change concentrations of solutions that may also be in that container. Now, if the partial pressures of the gases increases, then the total pressure of the container will increase. And according to Le Chatelier's principle, the equilibrium should then shift to remove that pressure. Because, you know, Mother Nature, she's kind of lazy and she likes things to be low maintenance. And the way the system is going to reduce that pressure is to reduce the number of gas molecules in the container. So that when the volume decreases then, the equilibrium will shift to the side with the fewer gas molecules. In the scenario where we have an equilibrium established, let's say that we change the container volume. Let's say we decrease it. Our questions become, how will this affect the concentration of the solids, the liquids, the solutions, and the gases? How will this change in volume affect the total pressure of the solids, liquids, and gases? And will it affect the value of our equilibrium constant? Well, decreasing the container volume will increase the total pressure. That's Boyle's law. As pressure goes up, volume goes down. As volume goes up, pressure goes down. So there's an inverse relationship. And if the total pressure increases, then the partial pressures of all the gases will increase. That's part of Dalton's law of partial pressures. Now, because the total pressure increases, the position of the equilibrium will shift to decrease that pressure by removing gas molecules. So that means it's going to shift to the side with the fewer gas molecules. And at this new equilibrium position, the partial pressures of the gaseous reactants and products will be such that the value of the equilibrium constant remains the same. So that's what happens. Well, we have another variable we could consider, and that would be that of temperature. And Le Chatelier's principle does ring in on this as well. And in this scenario, it looks at heat as like part of the, in an exothermic reaction, it looks at it as part of the products. It's not really a product, but that's where it gets written in an equation. So we can think of an exothermic reaction, it's one that releases heat, and because of that, we could think of the heat being as part of the products. And we would say that heat is acting as a product, and that increasing the temperature is very much like adding heat to the equation. And according to Le Chatelier's principle, the equilibrium in this scenario in an exothermic reaction would actually shift away from the added heat. So here we have an exothermic reaction in equilibrium, and let's assign some values because I want to calculate the equilibrium constant for this. So if we were to take the the concentration of the products right there and put it over the concentration of the reactants right there, we could get an equilibrium constant of 1.5 for this exothermic reaction in equilibrium. Even though we know that heat is over here, we're not going to worry with it because it doesn't go into our calculation. But if we do add heat to the product side, we know that it's going to cause a shift to the left in this equilibrium. So by adding heat to the exothermic reaction, what's going to end up happening is we're going to decrease the concentration of products because some of our products are going to be turned into reactants, and we're going to see an increase in the concentration of reactants because we got the conversion of the products. So let's assign some new numbers after having added the heat. So let's say that we used up 3 moles of our product, leaving us with 3 moles, and those 3 moles went over to our reactant. So now we have 7 moles of reactant. If we calculate a new concentration constant, we're going to see something very different. Now we're going to see that the concentration constant went down quite a bit because of the loss of the products. So from this we can then conclude that by adding heat to an exothermic reaction, it's going to decrease the value of K as a result of having lost some of the product and having seen a gain in the concentration of the reactants. So here we have our endothermic reaction, and let's go ahead and assign some values so we can calculate an equilibrium constant. So let's say we start off with a total of 6 moles per liter of reactants, and we also have 4 moles per liter of products. And we can plug those values into our equilibrium constant formula and actually get a number. So at the beginning of this, we have an equilibrium constant that is 0.67. Now, what happens if we add some of this heat in here? Well, we know that adding heat to an endothermic reaction is going to decrease the concentration of the reactants, and it's going to increase the concentration of the products because this reaction is now being driven to the right. It is favoring the production of the products. So what we'll see is a loss of our reactants because they're being converted to products. So we'll see that gain in our products. Now, if we take these values and do a calculation for a new equilibrium constant, we can see then that our equilibrium constant has shifted quite a bit and has gotten significantly bigger. And Le Chatelier's principle does predict that. So by adding heat to an endothermic reaction, we're actually going to see an increase in the value of our equilibrium constant. So to summarize this concept of tweaking the temperature and its effect on equilibrium, in an exothermic reaction, we're going to think of heat as part of the products. And if we increase the temperature, that's going to cause this exothermic reaction to shift to the left, because remember, heat is a product, it's going to be on the right. And as a result of this shift to the left, the equilibrium constant is going to decrease. Now, what happens if we decrease the temperature? Well, it's the same thing as pulling out products. And that means that it is going to create a shift to the right. And we're going to see the value of the equilibrium constant increase as a result of that. Now, the opposite is true in endothermic reactions. In the endothermic equation, we're going to think of heat as a reactant. And when we increase the temperature, in an endothermic reaction, we're going to see a shift to the right. So it's going to favor the production of products. So we're going to see more of our reactants moving into the products. And as a result of that, we're going to see a decrease in the equilibrium constant. If we decrease temperature in an endothermic reaction, it's going to shift to the left. It's the same thing as pulling out reactants. The equilibrium constant, therefore, will decrease. Now, we've talked a little bit about catalyst. What is the effect of a catalyst? on equilibrium? Well, catalysts are going to provide an alternative, more efficient mechanism, and they're going to work in both forward reactions and reverse reactions. Catalysts affect only the rate that the reaction occurs, and therefore catalysts do not affect the position of the equilibrium. They only affect how quickly you get there. Because think of this, remember our equilibrium is based upon either partial pressures of gases or the concentration of our gaseous products and our gaseous reactants. And catalysts do not participate in either one of those arenas. They're not part of concentrations or they're not part of partial pressures. So therefore, they don't affect anything.